All right, so in the video that I asked you to watch, we briefly reviewed enthalpy and entropy. A lot of this was reviewed from general chemistry. We said that enthalpy is a measure of the amount of heat released or absorbed by a reaction under constant pressure and volume. And we said when delta H is positive, the reaction's endothermic, and when it's negative, it's exothermic, meaning releasing heat. So for your problem of the day, you'll actually be tasked with looking at bond dissociation energies, table 6.1 in your textbook. I'll leave it up to you whether or not you want to work with kilojoules or kilocalories per mole. So just whatever numbers you pick, be consistent. You'll want to kind of follow the example I gave here where you make a list of bonds that are made and broken and then go through the same problem-solving process here. And then in addition, I said we don't really know much about a reaction by only knowing the enthalpy. In addition, we need to know about entropy. That's the measure of disorder. So we can quickly look at a system and measure disorder. If we're getting more moles of product, we know delta S is positive. If we're getting more moles of reactants than products, we know it's negative. And then if it's a tie at that point, we look at freedom of motion. If we're increasing the floppiness of a molecule, then the delta S is positive. If we're decreasing the floppiness, delta S is negative. And then we can start working with that. We said that entropy is closely related to temperature. And then to tie both of those two concepts together, meaning enthalpy and entropy, we look at Gibbs free energy. This tells us how spontaneous a reaction is. Does a spontaneous reaction necessarily mean that a reaction's quick? Nope. Did anybody watch the video? What was the example I gave in class about myself? What am I spontaneously doing? I'm spontaneously decomposing, right? That doesn't mean that it's happening fast, although it almost happened this weekend. Anyways, this just tells you eventually whether or not something will happen. It doesn't tell you the speed in which that reaction will happen, right? So that's what we're going to jump into today, is the other side of that coin. We're going to look at reaction kinetics. Kinetics is a direct measure of a reaction speed. How many of you remember talking about kinetics in Gen Chem? That's good. So let's make some notes here. Kinetics. First note is a reaction, a spontaneous reaction does not always occur quickly. Right? The forming of the Grand Canyon was spontaneous, but that took millennia to achieve, right? Millions of years to dig the trenches that are the Grand Canyon. So if we think about the rate of a reaction, we can factor in a few different things. One is this little k. We have to be really, really careful to show this as a little k, not a capital K. What's a capital K? That's an equilibrium constant, right? Little k is our rate constant. And then we can multiply this by the concentration of our reactants. So we'll put that in brackets. But let's indicate that this is our rate constant. And that this is our concentration of reactant. What about rate? How do we know the units for rate? Does anybody know? Can we know the units for rate right away? Not necessarily. We need to know the order of the reaction. So we'll talk more about that later, but the units for rate are closely tied to the reaction order. They're not a set unit, so we need to closely pay attention to that. All right, so let's make a couple of additional notes. What happens if we increase the concentration of our reactants? The rate's going to go up, right, according to this equation. Let's try to conceptualize why. Why would the rate go up if we increase the concentration of our reactants? Think about what's occurring within your round bottom flask or reaction vessel. Yeah, more things bumping into one another, right? So all of this is tied to molecular collisions. So note, when you increase concentration of reactive species, you increase the probability of collision. When you increase that, you get a faster rate. So it's really important to think about this not in terms of a math equation, but conceptually what's occurring in the flask. You've got a bunch of molecules running around bumping into one another. Sometimes when they bump into each other with the right amount of energy and the right orientation, they'll react, right? So the increased probability of them bumping into one another will increase the reaction rate. All right, there's a variety of different reaction rates that we need to consider. The first is what's called a first-order reaction. Does anybody remember what happens in a first-order reaction? What does it depend on the concentration of? One thing or two things? It's just one thing. So rate would be equal times K times the concentration of just one reactant within your round bottom flask. So let's say we have both A and B in your round bottom flask. What does that say about B? The concentration of B doesn't impact the rate at all, right? So we could have some unreactive species, or not even unreactive, but not species that impacts the overall rate. All right, so that'd be a first order reaction. Next one would be second order. And this can occur a few different ways. This can occur when A bumps into B, or it can occur when A bumps into A, so we'll just call that A squared, or it can occur when B bumps into B, which would be B squared, right? So all of these would be considered second order reactions, right? And then a third order reaction. This is a reaction where three things collide with one another. So this could maybe be A colliding with two B's, or it could be maybe two A's colliding with one B, or there could even be a third component. I'll just call this A, B, C. All of these would be examples of third order reactions, right? All right, so my question for you is, how can we predict a reaction order just by seeing one of these equations? Does anybody know a trick? So you're talking about limiting reagents. We'll talk about that next. Limiting reagents don't always impact reaction rates. Yeah, the number of reactants, right? So the reaction order is going to be equal to the sum of your exponents. So let's take a look at the first one. You see over here we've got an assumed 1 right there. So that would just be a first order reaction. Over here we would have a 1 and a 1. So if we add both of those together, that would be 2. Or we could just take the 2 given here in those other examples. So just by adding the exponents for every reactive species, or rate-dependent species, I should say, we can figure out the rate or the order of the reaction. Does that make sense? All right, so I'll give you a sneak peek about a reaction that we'll cover later. So we'll take a real-world example. And in this example, I've got this reactive molecule. What's this molecule called? Let's name it. And then check with your neighbor and see if you're naming it correctly. not quite. So longest backbone. We've got a group coming off here and here. What would this be called? It'd be 2-iodo, 2-methyl, then what? Propane. All right, so this is going to be one of our reagents. And in this reaction, I'm going to react it with this ion, right? So sulfur with the negative charge. And after we mix this together in our reaction flask, we know that the products that we isolate at the end have an SH covalently bound to the carbon now, and we have an iodide ion floating around. All right, so as a chemist, it's my job to figure out what rate the reaction occurs at, right? Is it a first order reaction, second order reaction, and so on? All right, so we could run a few experiments. So the experiment with changing concentrations. All right, so let's take an example. The first one, I'm going to double the concentration of SH- in solution. However, it has no effect on rate. All right, so what I do is then I double the concentration of my other reagent. And the rate doubles. Let's try to come up with some sort of rate for this reaction. So we know that the rate, it's always going to be some little rate constant. What should come after that rate constant, the little k? Should I have the sulfur reagent or the other reagent, or both? The other reagent, because we know the sulfur reagent doesn't impact the rate at all when changed, right? So it's not included in the reaction here. So we can go ahead and we can plug this in. And we can say it must be this rate. What does this tell us? Is this a first, second, or third order reaction? Okay, so it must be a first order reaction. And so let's kind of zoom out and look at this. Does anybody know what sort of reaction this is called? So some people would call it a displacement reaction, but what happened with that iodine group? It was replaced, right? Or some people might even call it substituted. So this is called a substitution reaction. We substituted iodine with our sulfur, right? So that makes sense. So chemists, when they were working on this, basically said, all right, this is a substitution reaction. With a nucleophile. We'll talk about what a nucleophile is later, but basically a nucleophile is something that has high electron density, or even better yet, a negative charge. So what do you think our nucleophile was in this case? The SH-. So the SH- in this case has a negative charge, so it was acting as the nucleophile in this reaction. So chemists, when they were looking at this, said, all right, let's call this an SN1 reaction. And what this means is it's code for saying that this is a substitution that involves a nucleophile. We call this nucleophilic. And then the 1 means it's a first order reaction. So chemists will study these reactions and then sometimes give them these codes to let us know a bit more information about them. Does that make sense? All right, what's the other really essential part of the rate equation? Besides first order, second order, third order, and concentrations? the rate constant, which we've kind of been ignoring so far. So tomorrow when we come back, we'll talk about factors that impact that little k, the rate constant. But make sure tonight that if you haven't watched that video from yesterday or the prior lecture, that you watch that and complete the practice activity, or pod, I should say.